Hello everyone. Today, I'll explain the concept of deadlock in operating systems, a fundamental challenge where processes become trapped in circular dependencies, unable to progress and blocking system resources. A deadlock occurs when two or more processes are blocked forever, each waiting for a resource held by the other. For example, process P1 holds resource R1 and waits for R2, while process P2 holds R2 and waits for R1. Since neither process releases what the other needs, both remain stuck indefinitely. We can understand deadlock better with real-life situations. Imagine a traffic gridlock, where cars block each other in a circle, no one can move until another does. Or two trains on a single track, each waiting for the other to pass. Even in chess, when no legal move is possible, the game is stuck, similar to a system deadlock. For a deadlock to occur, for conditions must hold at the same time. First, mutual exclusion, only one process can access a resource at once. Second, hold and wait, a process holds one resource and waits for another. Third, no preemption, resources cannot be forcibly taken away. And finally, circular wait, processes form a cycle where each waits for the next. A resource allocation graph helps visualize deadlocks. Processes are shown as circles and resources as squares. Arrows from a process to a resource show requests, while arrows from a resource to a process show allocations. If there is a cycle in this graph, a potential deadlock exists. Let's see an example. Process P1 holds resource R1 and requests R2. Process P2 holds R2 and requests R1. This forms a cycle, P1 to R2, then to P2, then to R1, and back to P1. This circular dependency guarantees a deadlock because neither process can continue. Prevention methods make deadlock structurally impossible. For example, require processes to request all resources at once to avoid hold and wait. Allow preemption so resources can be taken and reassigned. Or enforce a fixed order of resource requests to stop circular waits. Deadlocks reduce system reliability and efficiency. They can freeze applications, waste resources, and frustrate users. That's why modern operating systems carefully combine prevention, avoidance, and detection techniques to keep systems stable and responsive.